So, good afternoon. Lab 5 asks us to observe a bar magnet falling through a conductive, non-ferrous tube of aluminum foil, model the interaction between the magnet and the tube computationally in glow strip, and compare the computational results with the observational data. Now, we found that the average experimental time of the magnet in the tube was 1.468 seconds, while the computational time in the tube was 1.128 seconds. Now, the important physical principles that were observed in this lab were Faraday's law, which states that the changes in the magnetic field, i.e., the magnetic flux through a closed surface, produces electric fields that impart a force on the charges in the conducting wire, which generates an EMF and induces a current. Then Lenz's law tells us the induced current also produces an electric field that opposes the change in flux from the falling magnet to bring the system to equilibrium. And then Newton's second law tells us that a body's acceleration is directly proportional to and acts in the same direction as the net force on the tube. This is important to the lab because the tube of aluminum foil is modeled as a set of conducting rings centered on the magnetic dipole axis. This represents the closed surface through which the induced EMF and current will flow. This induced current in turn generates a magnetic field that opposes the change in magnetic flux, and then that magnetic field exerts a force on the falling bar magnet, which with this force counteracts the weight. Now the experimental procedure included determining the north pole of the magnet, dropping the magnet from an initial position just above the top of the opening of the tube, allowing the magnet to fall through the tube, recording and tabulating the time taken for the magnet to fall through the tube, and then calculating the average time. Now we expected that the bar magnet would fall more slowly through the tube. The measurements that had to be taken were the outer radius, inner radius, length of the aluminum tube, and the length of the cardboard inner tube as shown. Now this represents the time taken for the magnet to fall through the length of the aluminum tube over 5 trials. The average was calculated to be 1.468 seconds. Now the glow script code computationally models the falling of the bar magnet through a conductive tube using the magnetic moment obtained in lab 3, which was 2.809. Here, the bar magnet represents a point dipole and the conductive tube represents a stack of non-interacting conductive rings. From the video, we obtained the equation for the change in magnetic flux as shown and the Biot-Savart law to calculate the magnetic force on an object. So in this section of code, we calculated the magnetic field at a position r relative to the bar magnet. This section calculates the rate of change of magnetic flux through the ring caused by the falling bar magnet. The blue calculates the magnetic field of each ring. The pink section calculates the magnetic force exerted on each ring using the Biot-Savart law, which is equal to the magnetic force on the magnet. And the purple calculates the net force on the magnet, including the weight. Experimentally, we found that the average time in the tube was 1.468 seconds. Computationally, it was found to be 1.128 seconds. From the results shown on the side, we can see that the total experimental time in the tube was greater than the computational time in the tube. This computational time may be made more accurate by including the force of drag on the falling magnet, which would decrease the net force and acceleration, so time in the tube would increase. As seen, the shape of the graph shows that the velocity increases rapidly in the negative direction, reaches a maximum, then decreases gradually before plateauing at a constant velocity of about 0.26 meters per second. It can thus be deduced that initially the upward magnetic force on the magnet due to the loop is small in comparison to the weight. By Newton's second law, the net force is large, so the acceleration is large. Then, as the magnet moves down through the rings, the magnetic force increases and eventually equals to the weight. So the falling magnet reaches a constant velocity, that is, the net force is 0. This simulates the magnet falling through the aluminum tube. And whereas the purple was found to be anticlockwise and the red was found to be clockwise, these directions would remain the same if the magnets were flipped. Because as the change in B field, and therefore the change in magnetic field are negative in the y direction. So the induced current is anticlockwise. Lastly, if the resistivity in the conductor was reduced, the resistance in the conductor would be reduced. Thus, the induced current would increase. This would then increase the induced B field and the upward force exerted by the loop on the falling magnet. Physically, the magnet would fall more slowly through the tube. If holes or slots were cut through the tube, the induced current in the tube would decrease, therefore decreasing the magnitude of the induced B field and the upward force on the magnet due to the loop. This would increase the downward net force, so the magnet would fall faster. Thank you for listening.